Hey everyone, this is 11.3, which is on interpreting the shapes of data displays. We're going to introduce three different names of shapes. We've been hinting at this as we've been talking in our statistics unit, but then we're going to look a little closer at what happens to the mean when the shapes of the data displays change. All right, so our first example here is a box plot, and I'm asking you to figure out two things, to identify the median of the data set and to identify the mean. Hopefully you know that the median of the data set is a pretty quick and easy thing to find on a box and whisker plot. It is the value in the middle, or that line down the middle of the box, which sometimes isn't in the middle, but you know what I mean. So the median of this data set is 9, and then the mean of the data set is, I would have to add all of those values together in that list, 5, 5, 6, 8, 9, 9, 11, 12, 13, and 14, which I did, and I got 92, and then divide by how many numbers there are, which there are 10. So 9.2 is my mean. Now, where that would be located, it is not technically plotted on a box plot. You can't see the mean, but because we have that data above, we could. So the mean, if I were to imagine it, is probably right around in here. Okay, it's pretty darn close to where that median is. And if we were to describe the shape of this box plot, it's pretty equal on both sides. I mean, it's a little bit off kilter, a little bit more towards the smaller side, but most of it is pretty evenly spread out amongst those values. Now here is a box plot that is clearly not equally spread out. If you just take a quick glance, I love to look at the whiskers. I think those are the most obvious things to look at in a box plot. We have one very long whisker and one very short whisker. So this is almost the same data set, except for my numbers at the top end have now gotten bigger. So instead of it being 11, 12, 13, 14. Now we have 11, 15, 18, and 20. So we've got some bigger numbers over there. The median of this one is still 9. So we didn't change how many numbers there are or the location of that median. Now the mean, on the other hand, because those values got bigger, the mean gets bigger. So our mean, when we add all those values up, is 106. Divide by 10, our mean is 10.6. So now our mean is way over here. Okay, so we're going to have to make some inferences here in a little bit, but look at the difference between the distance between the mean and the median when we get this off-kilter graph a little bit. Let's look at one more example. Now we have an off-kilter graph the other direction. Our whiskers, again, these lines, we have a short whisker on the right side and we have a long whisker on the left side. The numbers at the beginning part of our data set got smaller, um, and we removed some of the bigger numbers on the right side. Okay, so let's first identify the median. The median is 8 this time, because we removed some of those bigger numbers. And the mean of the data, when I added all those values up, I got 70 divided by 10, which is 7. So my mean is now lower than my median. So my mean got pulled towards those smaller numbers. Look at another example. Here I have something that's a bar chart. You could call this a histogram, I suppose. We just don't have clear ranges on the bottom, but or intervals. But what this graph does is it calculates, or it shows the relationship between the mean and the median as I add more value or more data blocks. So I started with a very symmetrical, even graph, right? So I have, they're perfectly even on both sides. I could fold this in half and it would be the same. Now let's see what happens when I start adding values or blocks that are higher and make this not symmetrical anymore. So now what I have is this tail, as we call it, on the higher side of the graph. And you'll notice what that does is that moves the mean to be higher than the median. The median is still pretty close to where it was. It's not moving a lot, but these blocks have caused that to move to the higher side. Now, it doesn't matter where I put these blocks. If it is uneven towards the higher side, my mean is going to be higher than my median. I'm going to remove these blocks so we can see what happens on the other side. All right, so this time I'm going to add blocks on the smaller side, and I bet you can make a guess as to what's going to happen. As I move blocks to the smaller side and I make it so it's not a very symmetrical graph, I end up getting my mean pulled towards that smaller side. So my mean will always be less than my median if I have smaller values that are pulling that mean around. And we talked about that yesterday, how impacted the mean is by numbers that are farther away from the middle. Back at these examples that we talked about earlier, you can see when something is fairly balanced, your mean and your median are about the same. They're not going to be perfect, but they're about the same. When you have something that is off balance, and we will use the word skewed in here, your mean is going to change to be different or further away from your median. When it is skewed and you have more larger numbers, like these numbers that are far away from the median, or a longer tail in this situation, your mean gets pulled towards these bigger numbers. So our mean is getting pulled towards the tail, which is that longer whisker. When we have a longer whisker on the other side, my mean is getting pulled towards that tail. So my mean is going to get smaller than my median. My median isn't as affected as the mean is going to be. So if you were to guess where the mean would fall in this box plot, where would you think it would fall? Well, hopefully you notice that what we call the tail, or the longer whisker in this case, is on the bigger side. This is a not symmetrical graph, right? We have a lot of data. If you were to imagine this, we have a lot of data on this side, and then it kind of trails off on the other side. Our median is still here, right, where the bulk of our data is, but our mean is going to get pulled towards that tail. So our mean's probably going to be located somewhere in that area above the median. We don't know exactly where it is, but the important thing to know here is that it will be above the median. All right, so now we're going to put some words to this. We're going to call something symmetrical, skewed left, or skewed right. Okay, and then we'll talk about the mean. In this first graph, one of the helpful things to do a lot of times is kind of draw like a pretend little, curve above it. And what you want to look for is, where is that curve lower? Is it lower on the left? Is it lower on the right? Or is it lower on both sides? In this case, that curve, or the smaller side of the data set, is located on the left. So when that happens, we call this left skewed. You can also call it skewed left if you wanted to. It doesn't matter the order in which you say them. Now, when something is skewed left, what it's going to do is it's going to make the mean less than the median. It's going to pull that mean towards that tail because those smaller values are skewing that information. They're affecting that mean more than the median. Okay, here's the next one. This is a box plot. To me, this looks fairly symmetrical, all right? So we have pretty equal box or whiskers. Our median is right smack dab in the middle of the box. So I would call this symmetrical. Now, when something is symmetrical, the median and the mean are pretty darn close together, right? They may not be exact, but they will be almost identical. And last but not least, we have a histogram. So again, histograms, you can see the shape, but you could also imagine drawing like a little curvy line over it, right? It doesn't have to be perfect. But what you're looking for is, where's that curvy line going down or getting flat? Is it on the left? Is it on the right? Or is it on both sides? Our line is getting shorter or flatter on the right. Okay, we have the peak of the information on the left. So we would call this right skewed or skewed right. When this happens, the mean gets bigger than the median. All right, that mean is going to get pulled towards that data, and that data is on the bigger side, so it gets pulled to the right, which is up bigger. Here's an example of a word problem. The histogram shows the weights of all the dogs entered in a specific category in a dog show. I don't know why it's not clicking onto the next thing. There it goes. We want to state 3 possible values for the median. We talked about this earlier in class, possible values for the median. We're not going to know exactly where that median is going to fall, but we're going to do the best we can to figure it out. There are multiple strategies for this. The one I find students have the most success with is to imagine these as like little post-it notes or essentially dot plot, right? So each of these bars represents a frequency. So I'm going to cross out to find the median so that I can find it in the middle. It's not always in the middle bar, but sometimes it is, or the highest bar. So I'm going to cross out 2 on the left, and then I'll cross out 2 on the right. Okay, then I'm going to cross out, I'll change my color so you can see, well, that won't help. 2 on the left, and then 2 on the right again. Okay, I'm just going to kind of do 2 at a time to help us out. Let's do green. Now I'm going to do 2 on the right, which means I have to do 2 on the left. Okay, I'm just going to keep working my way in. 2 on the left and 2 on the right. All right, now you can see what I'm left with are in fact values in that middle bar. I could go 1 and 1 if I wanted to. It doesn't really matter what box it is in this bar, but what I can see is this bar holds the median value. So the possible median values would be anywhere from 30 to 39. So 30, 31, 32, etc., all the way to 39. It just asked for 3, but it could be any of the numbers in that bar. What shape does this data display have? Well, it doesn't to me look very symmetrical. If I were to imagine drawing like a curved line here, we get a little bit of a tail that is happening on the right-hand side. It's not much, but we get a little tail. So I would probably call this a right skewed graph because we have a tail on the right. Now, if we have a right skewed graph, what could we know about the mean? Well, the mean is going to get pulled towards the tail, so the mean is going to be bigger than the median. And the reason it's going to be bigger is because it's going to get pulled to the right, and numbers that are on the right are larger when we write them in order. All right, so now we are here to our notes. Now you could pause this video if you would like to, and copy the notes down from somebody that's not talking at you, or you can copy the notes here while I talk through them. Sometimes it helps people to listen as I write. So we're going to draw 3 examples of left skewed, symmetrical, and right skewed so you can know what they look like. We'll start with a box plot. A left skewed box plot will have usually a longer whisker on the left hand side. Some other things that you might notice is the median might be closer to the right side. So I did my best here to try to draw like an off kilter or not symmetrical median. That median isn't always going to be the things that tells us. Usually I look at the whiskers to help me out. In a histogram, you're going to have like a tail sort of thing on the the left, and then you'll have taller data on the right. So I tried to demonstrate that. It's not ever going to be perfectly obvious, okay, but you will notice that the left-hand side is shorter or smaller than the right. And similarly, in a dot plot, I'm going to get a smaller side on the left and a bigger side on the right. When you have left skewed data, the tail is on the left, which is that way, in case you don't know. When this happens, the mean is pulled towards the tail, so it is less than the median. It gets pulled to the left, so it becomes less than the median. Symmetrical data. everything's going to look pretty balanced. Now, again, it's not going to be perfect. No data is perfect, but you'll notice that the whiskers on a box and whisker plot are pretty much the same length. The median line will be pretty close to being in the middle. On a histogram, you'll notice usually that middle is higher and the outsides are smaller, so you get more of a what we call a bell-shaped curve. And similarly, in a dot plot, you'll notice that you get a higher amount in the middle and then it lowers on the ends. Okay, this is what we call symmetrical. When we have something that is symmetrical, the mean is about the same as the median. Okay, it might be a little bit above or a little bit below, depending upon, exactly where that data is located, but it's about the same. Okay, and then on the very opposite end of the spectrum from left, we have right skewed. Right skewed, you're going to notice you have a long whisker on the right. You are going to notice that most of your data in a histogram is on the right, but you have this, or sorry, on the left, but you have this tail on the right. You will notice in the dot plot, you will have more data on the left, and you will get a tail-like situation on the right. All right. So in right skewed, the tail is on the right, which is that way, in case you weren't sure. And then that pulls the mean away from the median. And so the mean is greater than the median. Let's look at a couple examples down below in your notes, or one example and then to try this. Okay, what do you know about the mean compared to the median in these? So we have heights of males in both Indonesia and in Netherlands. And again, we know the median. I know the median in this example is 158, right? Because it's a box plot, so I can see that right here. Boom. Now, I don't know the mean. I don't have the data, so I can't calculate the mean. So if I were to make an estimate on this, I would want to know what is the shape of the graph, and then that would help me know about the mean. So I'm going to look here and I'm going to notice that this whisker is a little bit longer than that whisker. I also notice that this median is a little bit closer to the left-hand side. So what I'm picturing here is that I have more data on the left. I'm just going to draw a quick, on the right, if you will, and less data on the, oh, I have more data on the left and less data on the right. Oh my goodness, directions are hard. So I personally would call this skewed right. Okay, my tail would be located on the right. So when it's skewed right, my mean is going to get pulled to the right. So I would guess that my mean is bigger than the median. I don't know what it would be, but it's going to be bigger than 158. Okay, the heights of Netherlands. Now this is a dot plot, so technically I could figure out the exact answers for both of these if I wanted to do the calculations, but I don't particularly want to do the calculations. What I notice here is that this, if I were to draw kind of an imaginary curve around this, this is actually pretty symmetrical. When something is symmetrical, we know that the mean is equal to the median. And again, we could calculate those exactly as to what they are, but we don't need to. We just want to compare the mean to the median. So they're about the same in this situation. Okay, now you can go ahead and do this. Try this. What is a reasonable guess for the median?